Show by the principle of mathematical induction that for all n belonging to the set of natural numbers, x raised to the power of n minus y raised to the power of n is divisible by x minus y. Okay, let us begin. So here we are given with a statement that x raised to the power of n minus y raised to the power of n is divisible by x minus y. So we're going to denote that statement with p of n. So let p of n be the statement given by, so we're going to express the statement as p of n such that x raised to the power of n minus y raised to the power of n is divisible by x minus y. Fine. So we're naming this statement as p of n. Now our goal will be to prove that this particular statement is always true for any natural number that we choose. For instance, let's say if we choose n to be equals to 3, so we have to show that x cube minus y cube is divisible by x minus y. If we choose n to be equals to 7, then x raised to the power of 7 minus y raised to the power of 7 is also divisible by x minus y. Okay, so how do we prove that this is a true statement? Now what we will do, we will first check that the given statement is true for n equals to 1. Now for n equals to 1, p of 1, the statement is now going to become x raised to the power of 1 minus y raised to the power of 1. We're saying that this particular expression is divisible by x minus y. Now, is this a true statement? Yes, this is definitely a true statement. So this tells us that p of n, this statement is true. This is a true statement for n equals to 1. That means if we choose the first natural number 1, then the given statement is going to be true. However, we want to check that it is true for other natural numbers as well. So what we will do, we are now going to consider a natural number m. That means we're going to choose n to be equals to m such that p of m, the statement p of m, this is true. We're going to consider this to be a true statement. Fine. Now, if this particular statement is true, this simply means that p of m, the new statement, is going to be x raised to the power of m minus y raised to the power of n. So this particular expression is divisible by x minus y. So we are considering that this is a true statement. Now, if this is a true statement, then it must be also true that p of m plus 1 is also true. That means we're going to consider the next consecutive natural number to that of m. So to show, our goal will be to show that p of m plus 1 such that what we have, x raised to the power of m plus 1 minus y raised to the power of m plus 1, this is also divisible by x minus y. Fine. Now how do we show that this is divisible by x minus y? We will take the help of the statement number 2. So let's take the help of statement number 2. So from statement number 2, we have already assumed that x raised to the power of m minus y raised to the power of m is divisible by x minus y. So that means x raised to the power of m minus y raised to the power of n. So this particular expression can be also expressed as lambda times x minus y. This simply means we are telling that it's divisible by x minus y, where lambda is some constant, and this constant belongs to the set of natural numbers. Fine. So let's label this as number 3. We're going to take the help of 3 now. So what we'll do, we will start with x raised to the power of m plus 1 minus y raised to the power of m plus 1. Let's use this particular expression. We have x raised to the power of m plus 1 minus y raised to the power of m plus 1, and we'll show that this is indeed divisible by x minus y. So how shall we do that? So first, we're going to rewrite each of the terms as x raised to the power of m multiplied to x. We have used the laws of exponents. So the second term becomes y raised to the power of m multiplied to y. Now let's do one thing. Let's take x raised to the power of x as the common factor from both of the two terms. So that means in the first term, we'll have x raised to the power of m minus y raised to the power of m times y over x in the second term. Now what we'll do next is we are going to add and subtract an extra term here. So let's say that the extra term that we are subtracting is y raised to the power of m, and we are going to add y raised to the power of m to it. Now, and then we have the remaining term, negative y raised to the power of m times y over x. Now the reason why we took this extra term, because from the first and the second term, what we can do here is we can replace x raised to the power of m minus y raised to the power of m with lambda times x minus y. So that means we have the first and the second term combining to give us lambda times x minus y. Added to, now we can take y raised to the power of m as the common factor from the third and the fourth term. So if we take y raised to the power of m, that will get multiplied to 1 minus y over x. Fine. Now we have x multiplied to lambda times x minus y added to, now 1 minus y over x. What is that? So we have y raised to the power of m multiplied to 1 minus y over x. So that's simply going to be x minus y divided by x. Fine. Now let's multiply throughout with x to get lambda times x multiplied to x minus y added to y raised to the power of m times x minus y. So now we have two terms, and in each of the two terms we have x minus y as the common factor. So let's pull that out. So we have x minus y. Now this is going to get multiplied to lambda times x added to y raised to the power of m. So we have considered m to be some natural number, and lambda is also a natural number, which means that this entire expression is some natural number. We don't have to worry about this value as long as it has a factor of x minus y. This simply tells us that we started out by considering x raised to the power of m plus 1 minus y raised to the power of m plus 1, and using the fact that x raised to the power of m minus y raised to the power of m can be expressed as lambda times x minus y, we were able to deduce that the expression also can be divisible by x minus 1 because it has a factor of x minus 1. So this simply tells us that the statement p of m plus 1, so this is actually a true statement. So this is a true statement. Now, if this is a true statement, let's write it down. So this is a true statement. If this is a true statement, then we can generalize. We can now generalize and say that p of n, the original statement that we considered to be as p of n, the p of n is going to be true regardless of the n value that we take. That means it is going to be true for all values of n, for all values of n belonging to the set of natural numbers. So any natural number that we took, the statement p of n, statement p of n, which is defined as x raised to the power of n minus y raised to the power of n is divisible by x minus y, it's always going to be a true statement. So here we have successfully used the principle of mathematical induction to verify our case.